Welcome. In this video, we begin Chapter 2, Sequences and Series. We begin with a motivating section, 2.1, Rearrangements of Infinite Series. It's kind of cool. It shows some crazy things that can happen and motivates the rest of the chapter. And then we begin in earnest with 2.2, The Limit of a Sequence. The big idea is convergence. If we can really understand convergence, then, well, that's what much of real analysis is all about. 2.1, Rearrangements of Infinite Series. So a series is when you add together things, and an infinite series, well, you add together infinitely many things, and weird things can happen. Take a look at this example. I have the infinite sum, n goes from 1 to infinity, negative 1 to the n plus 1 over n. When n is 1, then my solution is just 1. When n is 2, this becomes minus a half. When n is 3, plus a third, and then minus a fourth, plus a fifth, minus a sixth, and so on. Now, if you add this series left to right, you get a number that's about 0.69. But something funny happens. Let's imagine you take half s. All right, so I just halve all the terms of the sequence. So 1 becomes 1 half. The minus 1 half turns into a negative 1/4. The plus a third is plus a sixth. The minus a fourth is minus an eighth, and so on. So I can take half of that sum. And then we will add s to it. Take our original sum. So the thing that I had originally, 1 minus a half plus a third minus a fourth. And let's add these together. So I'm just adding straight down, and I end up, well, of course, half s plus s equals 3/2 s. So I end up with something bigger. And so adding straight down, 1 plus a third, minus a half, plus a fifth, the sixths cancel out, plus a seventh, and so on. And do you notice something weird about this 3/2 s? It is the original terms in a different order. That is crazy. This 3/2 s has exactly the same terms as my original summation, but just in a different order. And so, rearranging terms produces a value 3/2 as big. That's crazy. Here's the lesson. Addition in the infinite setting is not commutative. We have to let go of our intuition. We want what we know to be true about finite sums to also be true about infinite sums, but it's just not so. We have to lose our intuition and be really careful. Here's another example. The summation n goes from 0 to infinity of the powers of negative 1/2. So 1 minus a half plus a fourth minus an eighth plus a 16th, and so on. It turns out that in this case, every rearrangement yields the same sum, 2/3. No matter how I flip these terms around, the sum will always be 2/3. So what's going on? Infinite addition is commutative in some instances, but not others. So part of what we'll do is try to answer the question, what's the difference? How do I know if an infinite sum depends on the order of its terms? How about the associativity of sums? Let's take this simple infinite series, negative 1 plus 1, negative 1 plus 1, negative 1 plus 1, forever and ever and ever. If I pair together the terms, starting with the first two terms, well, let's see here, negative 1 plus 1, 0, 0, 0, 0. It really looks like the summation of this series is 0. On the other hand, what if we pair together the terms starting with the second term? So I have negative 1 plus 0 plus 0 plus 0 plus 0 forever and ever. It really looks like that sum is negative 1. So infinite addition is not associative. These weird things that go against our intuition, sometimes these are called pathologies. It is the pathologies that give rise to the need for rigor. Another statement in our book reads, "It may seem that progress is slow at first, but that is because we do not want to fall into the trap of letting the biases of our intuition corrupt our arguments. Rigorous proofs are meant to be a check on intuition, and in the end, we will see that they vastly improve our mental picture of the mathematical infinite." All right, so with that introduction, we are motivated to take a look at the rest of Chapter 2. We begin with sequences. So a sequence is an ordered list of numbers, and I use parentheses to indicate a sequence. So be really careful here, it makes a difference. I use braces to indicate a set, and I use parentheses to indicate a sequence. In sets, there are no repeats and order doesn't matter. In a sequence, numbers can repeat and order does matter. So here's an example of a sequence: 2, 4, 6, 8, forever and ever and ever. Here's another one: half, 2/3, 3/4, 5/6, on and on and on. So the first two sequences are given by explicitly listing the terms. I can give a formula for the terms of the sequence, kind of like a summation formula where I have a subscript and a superscript. N goes from 0 to infinity of 1 over 2n, so this turns into the sequence 1 over 1, well, just 1, followed by 1/2, followed by a fourth, followed by an eighth, and so on. Or I can indicate the sequence by putting just a sub n in parentheses, and then giving a formula for what that nth term looks like. So what is this sequence? Let's see, it starts with 1, so for all n in my natural numbers. So when n is 1, I get 2, and then after that 4, 8, 16, 32, and so on. The sequence on top diverges. It just goes to infinity, gets larger and larger and larger without bound. That second example is an example of a sequence that converges. The terms of the sequence look like they get closer and closer and closer to 1. Here's the official definition of a sequence. A sequence is a function whose domain is n. And that's kind of weird. Like, I look at this thing like, that guy, that's a function? And it kind of is. It shows us exactly how the function works. It's a function that takes 1 to 1/2. It's the function that takes 2 to 2/3. It takes 3 to 3/4, and so on. We don't actually use this definition of the sequence very often. Our intuitive understanding of the sequence will suffice. Let's talk about convergence. This is the most important definition in the course. I hope I made my point clear. You should memorize this definition as soon as you can. Here's the idea. I'll lead up to the definition in a second. I have a sequence of numbers, a1, a2, a3, and so on, and I also have some particular number, a. And I want to indicate somehow that the sequence converges to the number a. The idea is that I might set a certain barrier around a. Maybe let's call this an epsilon gate. I take some values that are epsilon away from a. So epsilon, I usually think of epsilon as a small positive number. So I look epsilon to the right of a, epsilon to the left of a, and I make a little gate. These are my parentheses there. And I ask myself, will it ever be the case that the terms of my sequence become trapped within the epsilon gate? And so I start looking at my sequence. A1, well, no, A1 is not within the epsilon gate. A2, A3, no, no, no. But eventually, there becomes a point where my subscript, we call it capital N or big N, I have a big N subscript where that sequence term gets within my epsilon gate. And not only does it get within the gate, but all the terms from then on out are trapped within epsilon of A. If that happens, then the sequence converges to A. Now, I need to be a little bit careful. It can't just happen for one epsilon. Maybe after that, I say, oh yeah, I picked an epsilon and I found a big N so that all my terms after the big N were trapped within epsilon. Then I pick a smaller epsilon. And I ask, I sort of play the game again. Is there some other big N so that after some point, all the terms of my sequence are trapped within that smaller epsilon of A? And if that's true, then I make an even smaller epsilon, and on and on and on. Basically, I want to know that for any epsilon that I pick, for any epsilon gate around A, is there some term of the sequence that eventually enters into that gate and it never escapes? The terms of the sequence never escape after that point? And if that happens, if that's so, then that's exactly what it means for the sequence to converge to A. Here it is in more official language. A sequence, the sequence of A sub n, converges to a real number A if, for every positive number epsilon, there exists a big N, that's a natural number, and I think big N will be a subscript of A. There exists a big N such that whenever N is greater than or equal to big N, it follows that the absolute value of A sub n minus A is less than epsilon. I usually read this by saying that A sub n is within epsilon of A. Right? See if you understand that. A sub n is within epsilon of A. My A sub n's are all inside the epsilon gate. Or you might read this as using the word distance. The distance between A sub n and A is less than epsilon. There are a few ways that we indicate convergence of a sequence. The arrow is common, I like this. The sequence A sub n converges to A, or I can use the word limit. The limit of A sub n equals A. Or I can say the limit as n goes to infinity of A sub n equals A. We'll often talk about the epsilon neighborhood of the number A. So again, I kind of have this number A, and I think, well, let's look epsilon to the right of A and epsilon to the left of A, and all the x values within that region. It's just a set. It's the set of all x such that x is within epsilon of A. The idea of convergence is that we say that the sequence converges to A if the terms of the sequence sort of end up in that epsilon neighborhood, no matter how small we make epsilon. Right? For any epsilon, I can make an epsilon neighborhood, and eventually all the terms, all the ending terms of my sequence end up in that epsilon neighborhood. One more way of thinking about this definition. Here's a concise way of expressing convergence. The sequence A sub n converges to A. Another way of saying that is, for all epsilon greater than 0, there exists a natural number big N such that n greater than or equal to big N implies A sub n is within epsilon of A. For all epsilon greater than 0, there exists big N, a natural number, such that n greater than or equal to big N implies A sub n is within epsilon of A. This is kind of cool because it looks like a horrible mashup of symbols, and you can write this down for one of your friends and really impress them. But it's also kind of a good way for you to practice the definition of convergence. 2 or 3 times a day until it's memorized. Write this down, look at it, and think about it. Write down the picture, look at the picture, and think about the picture. Memorize this. It will help you understand it. The more you understand it, the more readily you can remember it. All right, it's back and forth. Go back and forth between the memorizing and the understanding. Okay, let's do an actual example. Example 1. Let A sub n equal n divided by n plus 1. So that's one term of my sequence. Let's prove that that sequence converges to 1. And just for reference, I've written up the definition of a convergence there on the right, so we can refer to that. I always prove these types of problems using 4 steps, kind of always in a standard way. So let me introduce my method. So step number 1 is I want to take that absolute value of the difference. There's the absolute value, A sub n minus the proposed limit, A sub n minus 1, simplify it as much as possible. So if n is a natural number, the absolute value of A sub n minus 1, that equals the absolute value of n over n plus 1 minus 1. Use algebra. That stuff inside simplifies to negative 1 over n plus 1. Now the absolute value of a fraction is the absolute value of the top divided by absolute value of the bottom. So that's 1 over n plus 1. And notice that the absolute value of n plus 1 is just n plus 1 because n is a natural number. N is 1, 2, 3, or things like that. Now, I've gone as far as I can with simplifying with equality. Let me show you one more thing I can do, and I'll ask you to sort of believe me for now, and I'll explain why I do this in a second. But I'm also allowed to introduce a less than, or a less than or equal. And I continue simplifying my expression. So the 1 over n is just a little bit simpler than 1 over n plus 1. And you can see that when my denominator gets smaller, the fraction gets bigger. So I really do have a less than inequality there. And here's where I wanted to end up. I wanted to end this whole string of equalities or inequalities, I wanted to end it with an expression that has an n, so that as n gets bigger, the expression gets smaller. Surely, as n gets bigger, the fraction 1 over n gets smaller and smaller. Because what I want is, I want that absolute value to become arbitrarily small. And so I kind of ask myself, if epsilon is given, how big do I need to make the n so that 1 over n is less than epsilon? Well, let's let an epsilon be given. So here's step number 2. Let epsilon greater than 0 be given. The 1 over n is going to be less than epsilon precisely if n is greater than 1 over epsilon. Do you see that? I take sort of what I want, 1 over n less than epsilon, and you can get the resulting inequality by either taking the reciprocal of both sides and flipping the inequality, or you can multiply both sides by n and then divide both sides by epsilon, remembering that n is positive, epsilon is positive. Remember your rules for multiplying and dividing with inequalities. But I find that actually what's useful is the reverse implication. If n is greater than 1 over epsilon, then 1 over n is less than epsilon. All right, let's introduce the big N. So step number 3, introduce the big N. There exists a big N, that's a natural number, such that big N is greater than 1 over epsilon, right? 1 over the epsilon was just given to us. It's some positive number. 1 over epsilon is some real number, and it's the Archimedean property. The Archimedean property says, given any real number, there's some natural number that's strictly greater than that arbitrary real number. Well, if big N is greater than 1 over epsilon, and if I let little n be greater than or equal to big N, then little n must be greater than 1 over epsilon. Oh, and now I can use the reverse implication. If little n is greater than 1 over epsilon, then 1 over n is less than epsilon. So 1 over n is less than epsilon. Now, step number 4, I can tie it all together. Here we go. For all little n greater than or equal to the big N, the absolute value of a sub n minus 1 is less than 1 over n. Now this first inequality, that comes from step number 1. Absolute value of a sub n minus 1 is less than 1 over n. The second inequality, 1 over n less than epsilon, see, if n is greater than or equal to big N, 1 over n is less than epsilon, that comes from step 3. And we really have it. That was, it might be a little surprising, but we've actually done it. We put all the pieces together that prove that the limit of the sequence is 1. Let's just trace through. I said, let epsilon greater than 0 be given. Then there exists a big N with a certain property that for all little n greater than or equal to big N, the absolute value of the nth term minus the limit is less than epsilon. And that's reflected exactly in the definition up above. So I can conclude that my limit really is 1. It's a little weird. I mean, it's very weird. The first time you see these things, it always seems a little confusing. There's a lot of moving parts. There's a certain choreography to this, but it all fits together nicely. Pause the video, kind of study this thing, think about the logic of it. See that you can believe step 1. See that you can believe step 2, and then believe step 3, and then see how step 4 pulls them all together. I'll do one more example. Example 2. Let's look at a sub n equals 3 cosine n divided by n, and we'll prove that the sequence with these terms converges to 0. So step 1, let's take the absolute value a sub n minus 0. If n is a natural number, then the absolute value of a sub n minus 0 is the absolute value of just a sub n. That's the 3 cosine n over n. I can split absolute value across the top and the bottom. N is positive anyway, since it's a natural number, so absolute value of n is just n. And on the top, I have 3 times cosine n. Also, the absolute value of a product is the product of the absolute values. Now, maybe you see that cosine of n, I can't really do much more with this in terms of equality, getting something simpler, but with an inequality, I can say that the absolute value of cosine n is less than or equal to 1. And so my whole expression up above becomes less than or equal to 3 over n. And I've accomplished what I want to in this first step. I have a simple expression that has an n, and as n gets bigger, this expression gets smaller. And so now, for the next step, I'm kind of thinking to myself, if epsilon is given to me, if some epsilon is given, how big does that little n have to be to make 3 over n less than epsilon? So let's answer that. Let epsilon greater than 0 be given. Observe. 3 over n is less than epsilon precisely when n over 3 is greater than 1 over epsilon. I'm not there yet. Precisely when n is greater than 3 over epsilon. So basically, I'm going to always start with an expression like this, which is my ending expression with a less than epsilon tacked on it, and I want to end with an expression that is solved for n. So take your inequality and solve it for n. And as before, what's going to be important for us is the backwards implication. If n is greater than 3 over epsilon, then 3 over n is less than epsilon. Let's introduce the big N. That's step 3. There exists a big N, that's a natural number, such that big N is greater than 3 over epsilon. That's the 3 over epsilon I ended up with in step 2. And if a little n happens to be bigger than or equal to big N, then little n is greater than 3 over epsilon. And so, by step 2, the backwards implication up above tells us 3 over n is less than epsilon. Okay, let's put these pieces together in step 4. I know that for all n greater than or equal to big N, the absolute value of a sub n minus 0 is less than or equal to 3 over n. That first inequality is given from step 1. Absolute value a sub n minus 0 is less than or equal to 3 over n. And 3 over n is less than epsilon, and that was step 3. Thus, the sequence converges to 0. Reading back through, let epsilon greater than 0 be given. There exists a big N, that's a natural number, with the property that, for all little n greater than or equal to big N, the absolute value of a sub n minus 0 is less than epsilon. And there it is. We were able to prove that this sequence converges to 0. Divergence. A sequence that does not converge is said to diverge. And there are 2 ways that a sequence can diverge. In this first example, the terms of the sequence just go higher and higher and higher. They diverge to infinity. In the second sequence, negative 1/2, 1/2, negative 1/2, 1/2, negative 1/2, 1/2, the terms just bounce around. They never actually get arbitrarily close to some number. How does the definition of convergence fail for these? Well, maybe I'll look at the second one. Maybe I can imagine my term negative 1/2, and there's a positive term 1/2. And if I pick any number, I don't know, let's just say 0, but you can choose any number, you can form an epsilon around that number, sort of an epsilon neighborhood, an epsilon gate around that number, so that the terms of the sequence never get within that epsilon gate. So the sequence never converges to 0. But actually, now you're asking yourself, what if I actually chose, say, 1/2 as my point of convergence? Can the sequence actually converge to 1/2? So let's make our epsilon neighborhood around 1/2. What happens? The terms of the sequence, negative 1/2, 1/2, negative 1/2, 1/2. You know what? There are infinitely many terms within epsilon of 1/2, since they keep bouncing back and forth and back and forth. No matter how small you make epsilon, even if epsilon is tiny, it still contains infinitely many terms. But the problem is that there's no point after which all the terms of the sequence are within epsilon of 1/2. I'm always going to be having some terms that bounce out of that epsilon neighborhood. All right, our last point is uniqueness, and this is an example of how we might use the definition of convergence within the proof of a theorem, the proof of a fact. So the fact here is the limit of a sequence, when it exists, is unique. Here's a proof. Suppose, for contradiction, that my sequence a sub n converges to L and that same sequence converges to M, and that L is not M. So I might draw a little picture here about what I mean. I have a number L, I have a number M, and I'm imagining that somehow in some crazy world, the terms of my sequence get arbitrarily close to L after some point, and they get arbitrarily close to M after some point in my sequence. Let epsilon be 1/3 that distance between L and M. So in the picture here, I'll divide that little segment into thirds, and so epsilon is 1/3 of the distance between L and M. And what I'll do is I'll actually continue that 1/3 on the left of L and to the right of M, and that's actually making my epsilon neighborhood of L and my epsilon neighborhood of M. Now, by definition of convergence, there exists a big N1 such that n greater than or equal to n1 implies that the nth term of my sequence is within epsilon of L. So after some point in the sequence, all the terms of the sequence are within epsilon of L. Similarly, there exists some big N2, so that if little n is greater than or equal to big N2, then the nth term of my sequence is within epsilon of M. Oh, well that seems to indicate that all of those terms would be within M, within epsilon of M. I mean, from the picture, right, it seems obvious that this can't happen. One more idea here. Let big N without a subscript, let that be the maximum of N1 and N2. Now, let's choose a little subscript N naught. So choose a subscript N naught that is legitimately as big, at least as big as that big N. So what do I know about that N naught? Well, A sub N naught is within epsilon of L, so A sub N naught is here. And A sub N naught is within epsilon of M. A sub N naught is here. Okay. Clearly this is ridiculous, but really what makes it ridiculous is the triangle inequality. So I'm going to finish the proof by using the triangle inequality to show that there's a contradiction. 3 epsilon happens to equal the absolute value of L minus M. And let's break this up. I do a little trick. I'm going to subtract A sub N naught and add A sub N naught. And so that's the same equality. But now I'm going to use the triangle inequality because the triangle inequality A plus B absolute value is less than or equal to absolute value of A plus absolute value of B, where L minus A sub N naught is my A sub N naught minus M, that's my B. And so this is less than or equal to absolute value L minus A sub N naught plus absolute value M minus A sub N naught. And since it's in absolute values, it's okay for me to switch the order of those two terms. But now look at this. That first absolute value, that's less than or equal to epsilon. That second absolute value, that's less than or equal to epsilon. So I add the two epsilons together, I get 2 epsilon. Wait a second, this is ridiculous. Look at the beginning and the end of this inequality. 3 epsilon is less than or equal to 2 epsilon. No, cannot happen, because epsilon is greater than 0. So with epsilon greater than 0, it is impossible to have 3 epsilon less than or equal to 2 epsilon. There's the contradiction, and that proves the theorem. The limit of a sequence, when it exists, is unique. All right, there's a lot here, 2.1 and 2.2. But let me emphasize again, the most important thing that you can do is understand convergence. It is foundational for the rest of the course. Memorize that definition of convergence and go back through our examples and see how we used that definition to prove convergence. Okay, I will stop there.